Metric is given by, in this case, 2 plus 4 plus 6.
But that's what
So you get 3 terms. 2
All right,
plus
right,
4, 6, 6.
I'm going at roughly 2/3 speed, but anyway. Well, hopefully it won't go down to a smaller fraction. Actually, we're in no rush. It's all right. Never mind. We're in no rush. All right, but let me just finish saying some of the open problems associated now with this. In the world of thinking about forms in momentum twistor space, the sort of amplitudinal world. So the second natural question is, we define this positive part, this pk, right? And then we do something with it. We intersect it with some m times k plane in order to find the amplitude and so on. But there's a very natural question, just what is the space itself, right? So in other words, how do I think about the configuration of Zs that has this property? I didn't give you the most invariant beautiful definition in terms of the winding numbers and so on, but I gave you an equivalent shorter one, which let me remind you, again, I'll just say for m even, just because I'm not lazy, but this is just the space I plus 1, I m half plus 1, all positive, and this 1, 2, 3 up to m minus 1 m, this sequence 1, 2, 3, m minus 1 n has k sign flips. So we can call this space, let's give it a name. I'm going to call it G sub k of mn. Okay? And the first observation is that, just a trivial observation, that G sub k equals 0, no sign flips of mn is just a conventional positive Grassmannian, G plus mn. Now, this is not 1,000,000% obvious, I guess, but the claim is that if I define it this way, that this stack of minors being positive suffices for all the minors to be positive. In other words, if I say it has 0 sign flips, that means that these are all positive. Okay, so I'm saying that a bunch of minors are positive, and the claim is that this stack of minors being positive forces all of them to be positive. Now, I don't know if, do you remember, Hugh, did these contain a cluster? Is there some cluster that contains all of these? I didn't think there was a cluster that contained all these, but I don't remember. Okay, anyway, so I don't know how obvious it is, but my memory is that there's not actually one cluster that contains all of these minors. So it's more minors than in a cluster, but there isn't one minor that contains all of them. I could be wrong about that. In any case, it's true. So all of these minors being positive does force all the minors to be positive. And so the space already for the space is interesting already for k equals 0, it's the positive Grassmannian. But for higher k, it's not the positive Grassmannian, it's some sort of windy version of the positive Grassmannian. And now we have all the same questions we had for the positive part of the Grassmannian. What's the analog of positive coordinates? How do we think about it? What's the boundary structure? Et cetera, et cetera. Okay? Okay, so oops, shoot. Hold on. Oh no, I raised half my secretary. All right, well, it's okay. I'll fill it in later. Okay. Okay. So let's get some feeling for what the simplest new version of this space looks like. So I want to look at what is G of k equals 1 of m and m plus 2. Okay? Okay, so let's begin by looking at this space for m equals 2. In other words, this is what would correspond to the NMHV. Okay, if m equals 1, k equals 4, this would correspond to the NMHV sector. So officially from the amplituhedron, here we're looking for, remember the amplituhedron is looking for an m times k form. Okay? But really, in the whole space, and so we have, m times k form, which in this case is just an m form. So this is the form from the amplituhedron is an m form. But the whole space, the space is 2 times m dimensional. And so amongst other things, we might want to know what is the sort of top form that has logarithmic singularities on, does such a thing exist? If so, what is the top form that has logarithmic singularities on all the boundaries of this new space? Okay? So this is now a 2m form. Okay? So I just want to give you some idea what these spaces look like, because it's likely that they have a kind of a richer structure. Well, for a reason that will become obvious in a second what I mean by richer structure than we've been used to in the positive restaurant. Okay. So, so this is the case at least we think we understand. But let's just look at what this space looks like. So let's choose m equals 2. So this space is the winding, the sign flip 1 of 2 and 4. So what is it that we're asking? We're asking for the minors 1, 2, 2, 3, 3, 4, and 4, 1 to all be positive. And that this sequence 1, 2, 1, 3, 1, 4 has 1 sign flip. And now this explains the choice for choosing such a small n equal to m plus 2, because if I make that choice, this is unnecessary, right? You see, I've already said 1, 2 is positive and 1, 4 is positive, so I cannot but have 1 sign flip. Okay? Sorry, and 1, 4 is negative. This is 4, 1 is positive, 1, 4 is negative, so I must have 1 sign flip. Doesn't matter what 1, 3 is. Okay? 1, 3 is positive or negative, this is going to have a single sign flip. So when n is equal to m plus 2, the sign flip condition is redundant. It's not needed. So that's why it's an even simpler space. So let's now look at this g of k equals 1 and 4 and 6. So now I have 9 conditions. So now it's all of these minors 1, 2, 3, 4, 1, 2, 4, 5. Right, control.
Sorry, Nima, what was it for k equals 0? You got the positive.
For k equals 0, I just got the positive part. That's right. For k equals 0, because for k equals 0, I have to have 1, 4 is positive. Okay, and then this is just the this is just the.
Why was it 1, 4 is positive and here 4, 1 is positive?
Because that's what we get when we say the sequence 1, 2, blah blah blah, 1, 4 has to have 1 sign flip. It forces 1, 4 to be the opposite sign is 1, 2. Okay, so that's this. So the sequence 1, 2, 1, 3 up to 1n has to have 1 sign flip. That means that 1n is the opposite sign as 1, 2 when k is odd. Okay, so that's why I have to have 1, 2. I have to have 4, 1 positive, 1, 4 negative.
Okay, but 4, 1 being positive is not part of the conditions. I thought that was.
That's part of the condition, which is good. So 4, 1 is positive, 1, 4 is negative. We have to have 1 sign flip. Okay. So we have to have 1, 2, 1. This sequence 1, 2, 1, 3, 1, 4 has to have 1 sign flip. In particular, if it has an odd number of sign flip, if it starts positive, it has to end negative. So 1, 4 is negative, 4, 1 is positive. Okay? Okay?
Okay.
Okay. So let's do this guy. So this is 1, 2, 3, 4, 1, 2, 4, 5, 1, 2, 5, 6, 2, 3, 4, 5, 2, 3, 5, 6, 3, 4, 5, 6, 6, 1, 2, 3, 6, 1, 3, 4. What's my last one? Oh, I don't know, 4, 5, 6, 1. That's what I missed, 4, 5, 1. Good, all right. Okay, so I have to say that all these guys are positive. And again, that this sequence, 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 3, 6, has one sign flip. So it's exactly the same thing. This is positive, that has to be negative. And so this one does not matter. Okay, if I have one sign flip, I don't have to say anything about it. So all of these things have to be positive, and that guarantees everything that I want. Okay, so now, since this is G, M plus 2, it's convenient to write these conditions in terms of the conjugate G2 M plus 2. Okay, so let's write in terms of the conjugate G2 M plus 2. And let's just see what it is in terms of the conjugates.
Sorry, Nima, I think I still. So I don't see how that sequence could have 0 sign flips if you're assuming 6.
I'm assuming here k equals 1. I'm not doing k equals 0. We can talk about k equals 0 later.
Okay.
I'm just doing k equals 1. For k equals 0, you have to have the usual sign. Okay, so we don't have this sign. For k equals 0, we have to have that 1, 4 is positive. We'd have 1, 2, something, and 1, 4 is positive. And then we have to say something, then we have to say that 1, 3 is negative. Okay, we have to say something about the sign for 1, 3. Okay. Here we don't. When k equals 0, we have to say that 1, 3 is positive. For k equals 0 and 1, 3 is negative for k equals 2. We have to say that. Okay. For k equals 1, it turns out we don't have to say anything. So it's not, yeah, so maybe your question is, it's not true. It's a funny thing about k equals 1 for n equals m plus 2 that the sign flip condition is automatic. It's not automatic for k equals 0.
Okay.
Was that your question?
Partially, yeah.
Okay. Yeah, anyway, yeah. So, all right. So let's look at the conjugate of all these guys. So the conjugate here is 3, 4. Of this guy is 1, 4. Of this guy, just the conjugate things in order. This guy is 1, 2. But this guy is 4, 1. Its conjugate would be, if it was 1, 4, it would be 2, 3. It's 4, 1, so it's 3, 2. So we have to say that all these minors are positive. Okay? And you see, what this is all the minors of the form odd, even are positive.
What is conjugate?
Sorry?
What is conjugate?
Oh, just this is just
the whole
the,
Grassmann? No.
yeah, this is just the corresponding, I mean, this is just the GKN, GN minus KN. Okay, so I'm just saying that the minors of one are the complementary minors of the other with sign. Okay, with sign correct. Okay, so if we do the next ones, you'll see the same pattern. So here we have 1, 2, 3, 4. So here it's a minor 5, 6. It's got to be positive. Here it's 1, 2, 4, 5. It's 3, 6. Here it's 1, 2, 5, 6. It's 3, 4, and so on. Okay. So in all cases, what we get for all m, this space gk equals 1 of m and m plus 2 is equivalent to some part of G2m, where instead of saying all minors are positive, we say all of the odd even minors are positive. So there's no ordering between the odd, just every odd and every even. Okay? It doesn't matter how how they're ordered relative to each other. Okay? All right. So okay. So this is a new space. It's not the positive Riemannian. And so that's the space we'd like to understand, except now we've set it in the sort of simplest context, okay? Just in G2, M, instead of saying all the minors are positive, we want to look at what the space looks like where all these odd even minors are positive. And I can just tell you what we know about this space so far. You can triangulate this. So let's try to compute the canonical form for this space. Okay, so that's something that we can do. I mean, as a physicist, when we have very little geometric imagination, we can certainly just try to find the form of logarithmic singularities on the space, look at the form, and let the form guide us to what the boundaries look like, and something about what to expect for the answer. Let me remind you about something about the positive Rachmanian, is that so gk equals 0 mn, okay, here the canonical form that goes along with it is this object with all the m by m cyclic minors downstairs. But for this purpose, what matters is that this form only has poles and no zeros. So this means that it's sort of simplex-like. I'll explain what I mean by that. Well, certainly we know the positive Rachmanian is the sort of Rachmanian cousin of the simplex. Right? You see, when we have a simplex, we have a simpler situation. Like if I have a triangle, if I want the canonical form that has logarithmic singularities on the boundaries of this triangle. So if this is the line 1 minus x minus y equals 0, and here's x and y equals 0, this canonical form is just dx dy over xy 1 minus x minus y. It's a d-log form of all the three boundaries. So this form has no numerator. Okay? And that reflects that it's just a simplex. That, for example, reflects that I can find simple positive coordinates that cover the entire thing. These are all related to each other, right? Very simple rational positive coordinates that cover the whole thing. On the other hand, the second I move to something more complicated, like a quadrilateral, here there are 4 lines for the canonical form. So it has to have 4 poles over L1, L2, L3, L4. But now this does have to have it's very important that it has an interesting numerator, because this canonical form, in order for it to only have singularities on the boundaries of the quadrilateral, and not on these artificial points that are not there as boundaries of the quadrilateral. See, if I just tell you that I have these 4 lines as boundaries of the quadrilateral, then the form doesn't know. It knows that the codimension 1, it knows that the poles are in the right spot, but in principle, when you sit on the locus of L1 equals 0, I could have poles when L2 goes to 0, when L4 goes to 0, but also when L3 goes to 0. Okay, and so that's bad. I don't want to have a singularity there. I don't want to have a singularity there, and so I have to have a numerator that is exactly puts a 0 through these 2 bad points. Okay, so this is the simplest instance of something that gets more and more sophisticated, even for polytopes, and beyond that for amplitude. But already you see that when the form has a numerator, that's an indication that it's not as sort of a simple object. You have to triangulate it. You have to build it up out of a bunch of pieces. There is not, for example, one rational set of coordinates to cover the entire inside of the quadrilateral, and so on. Okay? We'll talk in the afternoon about other kinds of maps into this thing, but there isn't a simple rational map, the analog of positive coordinates that covers the inside of the triangle. Okay, so what we can do is take the space and triangulate it. And we can triangulate it in a variety of ways. So let's go back to our problem where gk equals 1. So I can now say it in, so this gk equals 1, m plus 2, which is turned into this space in g2 m plus 2, where all the odd evens are positive. One way that you can triangulate it is we know that if all the minors were positive in some ordering, I know what the form is for that guy. That's the usual positive Rachmanian form for that. So what I can do in order to get just this one, I can triangulate the space where all the odd evens are positive by covering it with all the orderings, all the possible orderings, but all the orderings in which the odds are behind the evens, but otherwise interlaced anyway. Okay? So that's a natural way of triangulating this space. So already for m equals 2, there's nothing to do, right? For m equals 2, this is just the same as G24, it's just our usual form, there's nothing to do. But starting with m equals 4, I have to keep 1, 3, 5 on one side of 2, 4, 6, and otherwise interlace them any possible way. And there are 18 orderings. Okay, so we can take the sum of those 18 Park-Taylor D-log forms associated with each one of those orderings, and you can use that to get an answer. Okay. All right. So let me tell you what the final answer ends up being. In this case, m equals 6. So this is m equals 4. So n equals m plus 2 equals 6. So the form ends up being the following when I read it in G2M language. So it's some d2 times 6c mod GL2. It has now 9 poles. So it's not just, so it has 6, 1, and then also 1, 4, 2, 5, and 3, 6. But now it has an interesting numerator. It has an interesting cubic numerator, which in this case we can sort of simplify easily. And it's 1, 2, 3, 4, 5, 6. Minus 2, 3, 4, 5, 6, 1. Minus 4, 2, 5, 3, 6. Right. So that's the acclaim. Okay. So that's what you get when you sum over all these 18 regions. It collapses to it. Oh, damn it, did it again. All right, but let me tell you another cool interpretation of this guy. Remember, in general, we're looking for a 2m form. Right? This is the form on G2 m plus 2. But the amplitude, which somehow is tied to this space, right? I mean, after all, we have to take this space and then slice it with this subspace, blah, 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 to get this M form. The amplitude gives us an M form associated with this space. So what's the simplest guess for how I could get a 2M form? If I have an M form, I just square it. Okay, so the claim is that this omega 2M, which is the top form on this winding one space, is actually equal to omega 3 of the corresponding amplitude all squared. So those are what we know about this guy so far. Okay. This is a very different expression. This is an expression which is a much shorter expression. It's not sum over 18 regions. For example, for n equals 6, it's sum over 3 terms. Okay. It's a different formula, which still you reassemble, and in the end, this is the answer. But this is another interesting interpretation of what this is that somehow does tell you that this space, there are a variety of forms on it, and they're related to each other in an interesting way. So the low form, which we care about at tree level, is somehow related to this top form that knows about all the sort of winding structure. Okay, that's all we know at the moment. As I said, this is all in the spirit of telling you things we've been running into in this workshop in the past few weeks. But this is an indication, whatever this space is likely, I'm guessing, not covered by positive coordinates in an obvious way. Maybe you have to triangulate it. We just did triangulate it in one particular way. Maybe there are other ways of triangulating it. Maybe there are very clever choices of positive coordinates that I don't know how to think of yet, but certainly I've never seen, even in simpler settings, simple choices of positive coordinates that undo these numerators. Okay, so it seems like a more interesting space. Many other questions. What's the topology of this space? We know that the positive Riemannian is a ball. What are the topology of these winding spaces? I mean, there are millions of obvious questions that we ask for the positive Riemannian, but we can ask for these flippy spaces, and this is just some indication that there's some interesting structure at work. Okay, so that was open problem 2. Yes?
If you glue it to the positive part, does the third term in the numerator disappear?
If you glue it to the positive part, yes. If you glue it to the positive part, the third term of the numerator disappears. That's right. Yeah. So this kind of looks like 2 terms. This looks like, this looks like 2 orderings minus a third ordering. So each one of these terms is the canonical form for a given order. We could write it down. Okay? So if I kill 1, 2, 3, 4, and 5, 6, then down here I have 2, 3, 4, 5, 6, 1, 1, 4, 2, 5, 2, 6. for the first term. So this is the ordering 2, 2, 3, 6, 1, 4, 5. Okay? So that first term is that ordering, is what I get from this ordering. The second term is the same thing, cycled over 1, minus that, and then minus the usual positive part. Okay? So I don't know what that looks like. It's some region, and you take out something, you take out something else.
So does it touch the positive part in codimension 1?
Yes, touches the positive part in codimension 1. Yes. Yeah. So, I don't want to say anything. I don't want to say anything more about this because we don't know how these things are related. But if you guys remember, long ago, about a year and a half ago, 2 years ago, with Song and Mark, we were looking at these forms mod torus, okay, where you can now get a 3 form like you would for the icosahedron. And then there was somehow a picture that this form is associated with a torus, and the torus touched the icosahedron on the 3 square facets of the icosahedron. So we had this sort of inner tube picture where you had the icosahedron sitting inside this torus. Now, that's what you get after mod torus. We have no idea what that means about the topology of this thing upstairs before you mod out by the torus. Okay. But it's conceivable that it has some interesting topology just because it looks like you're taking some space and ripping some pieces out of it. So maybe that's it. I have no idea. Don't want to speculate.
So,
Yes.
one question. Is it true that all these forms are just like some power of this 2 form?
No.
And
Absolutely
times-
not. No. So sorry. What they're definitely not is powers of the 2 form. Okay. What I don't know is if it fits into the world of forms that Thomas was talking about
so that's
yesterday.
what I'm asking.
Of sort of D-logs of frozens and other things. That I don't know. But they're definitely not powers of the 2 form. That. Yeah. So this is. Yeah, I should say that this object has bedeviled us for a long, long time because we really wanted to make use of this in physics for ages, and there was just no natural home for it. It didn't work. It didn't match any actual amplitude. Well, now we know that its purpose in life is actually is the top form associated with this winding region. It's not directly an amplitude, but it's probably has some purpose in life. Okay, so let me now move on to the third open problem before I switch topics. The third open problem is to go back to loop positivity. For n equals, just for n equals 4. So now we're in that. This is a much simpler world. We just have all these a, b, I. Again, we naively say we have all these a, b, I, a, b, j are positive. And for n equals 4, this is just each one of these matrices, these rows A, B is a 2 by 4 matrix, I can write in this form that we talked about. Okay? Just to be very concrete. So in other words, we have all of the A, B, I plus 1s are positive, and that they're all mutually positive, which just for n equals 4 just means what I said, that all these x, y, z, w are positive, say, in this matrix thing, and all these minors where you take 2 of these things together are positive. The formula that I wrote down before. Okay. So this, if you have L lines, as I stressed before, this has the unusual feature. It has a little bit of ordering in it, the ordering for the columns, which gives us the usual positivity for these guys. But the heart of the matter, the interesting part, so this just says each one of the lines is inside the one loop amplitude by itself. But the interesting part is that they have to interact with each other. These lines have got to stay mutually positive to each other, all of them. Okay? Okay. And now this is some discussions started during Yara's first visit here. And that we've been discussing with a variety of other people since, is that, so this is a perfectly fine space, and there's a question that our mathematician friends always ask us, which is, great, you have all this stuff, you get this integrand, then you have to integrate, and then you finally get some polylogs and interesting functions at the end, right? So can you just give us one clean mathematical problem who takes us from geometry on one side to like polylogs on the other side? Just one problem where you don't have to say physics mumbo jumbo in the middle, okay? And we can do that, but the problem is that the questions for which we can do that are a little bit complicated, okay? They involve taking ratios of amplitudes, and then you can only start talking about it for k equals 1, so there's a lot of stuff going on. Even in the very simplest case, though, this case, n equals 4, right? But this part of the problem about the mutual positivity of lines is a giant chunk of the physics of n equals 4 scattering amplitudes, okay? For example, if you literally compute these amplitudes, they're logarithmically divergent. They are divergent, okay? So we can't actually compute the integrals, they're divergent. But there's a certain universal behavior associated with these things. If you actually carry out the loop integration, so if you carry out all these d4 times L integrals over all these ABIs, which are integrated over all of Minkowski space, let's say, for the ABs, you get something that's log to the 2L divergent. And then has a lot of subleading divergences from there. Okay? So it's incredibly divergent. But there's a very simple place where all the divergences come from. And I can characterize the simple place the divergences come from geometrically in the following way. We have 4 external points, Z1 through Z4. So here's Z1 through Z4. They kind of make this, they live in P3. They're not all in a plane, but anyway. And where the divergences come from is the following place. The divergences come when these lines, so there are also some lines here. There's some lines AB that are living, in general, all over the place. But in physics parlance, these are soft and collinear divergences. And you can say geometrically that these divergences arise from the region in that integration where these ABs have the property that first they pass through one of these points. So that's getting bad. Okay, so it's getting a little singular. AB passes through one of these points. But not only does it pass through one of these points, it passes through one of these points while lying in this plane, 4, 1, 2. Okay, so that's the sort of most divergent region you can have. Okay, so each one of those regions where AB is close to passing through 1, lying in the plane 4, 1, 2, gives you a log squared infrared divergences, and when you have L of them, you get log to the 2L. Okay, so that's, okay? And indeed, this region that we're talking about, it has boundaries there. Okay, so these are all boundaries of the region that we're talking about. Each one of these is some boundary of the corresponding positive Riemannian, if you like, for each one of the G24s. And there's nothing that stops me from putting all the ABIs together. They can all pile up on top of each other. L lines, all passing through that point, all lying in the plane, and that's where the divergences come from. Okay, so that's very well known. It's sort of very classic in physics. And there's a question you can ask. It's also very well known in physics that the amplitudes, that the infrared divergent part of the amplitudes exponentiate, and that it's a good idea to look at the log of the amplitude. So if you look at actually the log of the amplitude, so the amplitude kind of looks like some 1 plus g squared times something at 1 loop, plus g to the 4th times something at 2 loops, and so on, plus dot, 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 dot. So it's well known that if you look at the log of the amplitude, it just formally means I just expand this thing out, okay, as a power series expansion. So at begin here, the 1 goes away, at begin is g squared times m1 loop. For example, at g to the 4th, I'd have something that looks like m2 loop minus m1 loop squared. Plus dot, dot, dot. Okay? So it is well known in physics that if you take the log of the amplitude, the log is much, much better behaved. In fact, the log of the amplitude is only log squared infrared divergent instead of log to the 2L divergent. So it's still infrared divergent, but it's log squared divergent. And long ago, in the early work on the amplituhedra, we gave an amplituhedral interpretation of that fact, because if you ask can you build some function out of the amplitude that has the property that as many of these boundaries are killed, as many of these residues are killed as you send lines into this point lying through the plane? The answer is that yes, you can do it if you take this very specific combination, which is the log, and it has the property that in order to get any residue in this region of the lines passed through the point lying in the plane, you have to take all the lines in there together. Only if you do that, you get a residue. Otherwise, there's no residue there. Okay? Good. So that we knew for a long time. But there's a cool twist to the story, which actually we also said back then, but we didn't realize the sort of really the importance of. You can think of the log of the amplitude as actually this object is not a d-log form. I mean, I can write it, it's perfectly fine with some form, but it's not a d-log form. It has very interesting non-vanishing residues, non-unit residues that you take lots of singularities. You can get numbers all the way up to L factorial if you have L loops as you take residues as you go down. However, you can actually express this log of the amplitude as a sum over different regions in this amplitudinal space, where instead of imposing that all the ABI, ABJs are positive, you have different sign patterns. You allow different sign patterns. So let me explain it in the very simplest case of L equals 2, where what we see is something that looks like M2 loop minus M1 loop squared. See, so at 2 loops I have some AB, let's say AB1 and AB2, and the 2 loop region is saying that this thing has got to be positive, but I'm subtracting from that the 1 loop squared region. Now the 1 loop squared region doesn't care anything about the mutual sign between 1 and 2. So in 1 loop squared is just AB1, AB2 positive, and also AB1, AB2 negative. Just the sum over those two regions. And so if you subtract this from that, you actually kill the region where it's positive, and you're just left with the region where it's negative. Okay, so the log of the amplitude is a different region in the amplituhedron, where AB1, AB2 is negative instead of positive. Okay, so the cool observation that, is that, in fact, there are tons of regions like this. Not just one region, but at L loops, you just sort of imagine you plunk down, L ABs, and you just draw the complete graph between all of them. So I have to say something about these signs, okay? And the claim is all you have to do is say that the only rule is that for every AB, there is at least one CD for which ABCD is negative, and that's it. Okay? So there are lots and lots of possible sign patterns you can choose, but there are those sign patterns for which every loop has somebody that is mutually negative relative to. Okay? Now the claim is that every one of these regions individually is some geometry. There's some d-log form associated with it. These are honest d-log forms, so they're not like the log of the amplitude is not a d-log form, right? It's a sum of d-log forms with funny coefficients. Each one of these regions is honestly a d-log form, and it has the property that if you integrate it, you would get something that's only log squared divergent. Okay? Okay, but in fact, that means that if you step one back from this, you actually get completely finite integrals that we could talk about. And this gives us a set of objects that we can explore in n equals 4 super-Yang mills that are polylogarithmic functions of a single variable, which I'll now explain. So what I want to do is take any one of these regions, and what we're going to do is integrate. I'm going to choose one of any one of the lines AB to be special. So I'm not going to integrate over that line, but I'm going to integrate over all the rest of them. So d4 times L minus 1 of all the rest of them. Okay, if I do this integral for this form associated with one of these sign pattern regions, I'm now going to get a finite function Okay, and it's just a function, completely finite function of my external data 1, 2, 3, 4, and this last line that I've not integrated over. And in fact, there's only one invariant that we can talk about, which is this cross ratio. AB12, AB34, let's say, over AB13, AB24. Okay, so if I call this object Z, what we now have is a map between some region in some generalized amplitude. So you give me one of these complete graphs with some correct sign pattern so that everyone is connected to somebody, everyone is connected with a minus to someone. So from any one of these pictures where everyone connected to someone else with a minus, from any one of these, if you choose one of these and integrate over the rest of them, we're going to get a finite function of a single variable z. Now, if you wanted to, this is going to be a polylogarithmic function, a pure polylogarithmic function. So it's going to be a pure, in other words, the coefficients will be 1. All of the discontinuities will be 1. Okay? Unlike, again, what we got with the actual log of the amplitude, which has funny numbers in front of it all over the place. But now we can, the idea is that we can naturally subdivide the problem into the part that's naturally geometrical, and then assemble all these regions together into the log if we care at the very end to get the right answer. That has some sort of trivial combinatorics associated with the expansion of log. Okay? But purely geometrically, every one of these regions is associated with a finite function, a finite polylogarithmic function, and it would be interesting to learn how to compute it. First, to compute it in examples, but then to see whether the underlying geometry is reflected in some way in the polylogarithmic structure of this guy. What I want to say is that this, I believe, is the simplest set of polylogs associated with n equals 4 super mills. Canonically associated with n equals 4 super mills. There's not just one of them. You would not think of this. I want to stress, if you're just playing with the amplitude, the only object you can build out of the amplitude is the log of the amplitude. Okay? None of these pieces are obviously associated with the amplitude itself. They're obvious from the geometry. They're not obvious from the amplitude. And the log is a sort of a complicated object, as I said. These look like the simple building blocks out of which they are built. And it would be really interesting to understand what they look like. I can just tell you what the first example of this guy is. Notice that the cyclic symmetry of the problem says that z goes to 1 over z under a cyclic shift. And so the first interesting example is just at 2 loops, where we literally take this region AB1, AB2, negative, and I just integrate over dAB2. And what I get out of this is pi squared over 6 minus log squared z. So that's our first rather trivial weight 2 log associated with this. And this idea to take the log of the amplitude and integrate everything about one loop momentum and get an interesting polylogarithmic function, and then to integrate this at the end to extract the infrared divergences goes back to work of Fernando Alday and Johannes Hahn from 5 or 6 years ago. The sort of novelty here is that we're now liberating it from the amplitude. We don't care about the log of the amplitude. There's just a natural question associated with the geometry of the amplituhedron where we have these different sign regions. And so long as we just ensure that everyone is connected with someone else with a minus sign, it's guaranteed when we do the integral we get a finite expression. And it's an interesting question to try to understand what these finite expressions are. All right, so that's the third open problem. First, purely, even before doing these integrals, there's a larger space of regions we could care about, not where all these guys are positive, but where there's various sign patterns for them. Trying to understand them is interesting, and a subset of those guys you can literally integrate to the bitter end and get something dead finite. Okay, so this is a completely mathematically well-posed problem. Whether it makes it easier or harder remains to be seen. Okay, any questions? All right. How long do I have, Lauren?
I don't know, 20 minutes, 25 minutes?
Okay. All right. Okay. Actually, so I think I can do something. Okay. Okay. So now I'm going to switch. Now I'm going to switch gears and talk about a second set of. I'm thinking about movies so much today, but these, whenever I draw this picture of the association, I think that I'm in the Blair Witch Project. Kids these days don't know anything. All right. Okay, so okay, so now we're going to ask the same kind of questions again, except in a different, for a different class of theories. Now the theories that we're going to talk about are much simpler. Okay, so the theories that we're going to talk about are the so-called this mouthful by adjoint phi cube theory. But all this is at least at tree level, it's an excuse to just draw planar graphs and just sum over planar graphs, but with the usual sort of Feynman propagators attached to them. So if I had 4 points, I would draw 1, 2, 3, 4, 1, 2, 3, 4. And I would write down this propagator 1 over P1 plus P2 squared, let's say for this guy, and 1 over P2 plus P3 squared for this guy. So this is directly associated with, so in a sense, this is something that has the quintessence of what's important about Feynman diagrams, which is the most important thing about the Feynman diagrams, which is the structure of all these poles, without all the complications of the numerators and polarization vectors and the rest of the complicated Feynman diagrams. And so this just captures, at least for planar theories, something universal about the singularity structure that every such theory has. Every such theory has propagators that look like that, or just care about these propagators and nothing else. Of course, there is some official Lagrangian that gives you this as its diagrammatic expansion, which is where the rest of this by adjoint words come from. But if you're a physicist, you care. If you're a mathematician, you don't care. So, or you don't care immediately. You might care a little later. Okay, so that's what we're talking about. And so if I go back to the picture I love talking about, if you imagine. Now, this is some imaginary world where your experimentalist is sitting there. They're just scattering these scalar particles together, and all they have access to is they have the invariants are just these variables pi dot pj. So we call these Sij or pi dot pj. That's all you have access to as experimentalists. You're just moving these invariants around. You're moving them around, and you detect some interesting things about the structure of the answer, right? You move these things around, you get objects that have some interesting properties, and you wonder what it is that's going on inside. Okay? And this is a very, very simple case where we have a canonical answer for what's going on inside, which is that we just draw these tree graphs, right? We just draw these trivalent tree graphs, and we sum over all the propagators, all the 1 over p squareds that we see. Okay. So in this case, at least for this theory, the kinematic space is these guys. The space of these Sij's is the obvious kinematic space. And we'd like to ask a question in this space directly, without talking about the interior of the space-time, the finite diagrams, all the rest of it. We'd like to ask a question in this space whose answer gives us the same thing. Okay? Now let me actually clean this up a little bit, because these Sij's are still not quite ideal, because they're a little bit redundant. I mean, they satisfy identities. So if I sum over all the j's of these Sij's, I get 0. That's the statement of momentum conservation. So there's a better thing to do, which you see many times in this business. If we have an ordering on the external particles, which we do, we're drawing these planar diagrams, then we can draw this polygon, P1, P2, up to Pn. And now, it's natural to look at the only propagators we see in these planar diagrams are sums of consecutive momenta. So there's some distance between some point I and a point j in this picture, which we can call xij, which is pi plus dot 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 plus pj minus 1, all squared. Okay, and of course you'll notice that xij is equal to xji. So that's something nice. If I just give you the chord, I've told you whether it's P1 plus P4 or P5 plus Pn, which are the same. But I'm more invariantly labeling it just by this way of breaking apart this polygon into two. Okay? And furthermore, this is exactly, the number of these xij's is exactly the actual number of independent kinematic invariants. Okay? Again, how many kinematic invariants do we have? Naively, so the number of kinematical invariants is the Sij's minus the n conditions for momentum conservation. And this, of course, is exactly, this is n choose 2 minus n. This is nn minus 3 over 2. But of course, this is also the number of diagonals of the polygon. And so on, right? At the same counting. The total number of edges minus the ones on the outside. Okay, so first of all, these are just better variables. So the kinematic space for this problem is naturally just a space of all the x's. So let me draw it again. The kinematic space for n particle scattering is just the space of all xij's, which are associated with diagonals of an n-gon. And furthermore, if we were, let's just cheat for a second, just cheating, since we know the answer from Feynman diagrams, what is the amplitude? How do we think about the amplitude? Well, we think about the amplitude as the sum of Feynman diagrams. Let's say for n equals 4, or for n equals 5, we draw pictures like this. So here we would write 1 over P1 plus P2 squared, plus 1 over P2 plus P3 squared. But this is just, in terms of a nice variable, this is just 1 over x13 plus 1 over x24. Similarly, this one would be 1 over P1 plus P2 squared, P1 plus P2 plus P3 squared for the first term. Let me just write the first term, which would go to 1 over x13, x14, and that's something similar for the other diagrams. And so every Feynman diagram is just dual to a triangulation of the n-gon. So if you give me at 4 points, 1, 2, 3, 4, if I give this triangulation of the square, of course it's associated with this cubic graph dually. So I can go back and forth between the Feynman diagrams and the triangulations of the polygon. I'll go back and forth. I'll draw both of them as I find convenient. But if we use the language of triangulations, the function that we're supposed to be getting, again cheating because we know the answer, the function we're supposed to be getting, the amplitude that depends on these xij's, the amplitude that depends on these xij's is just the sum over all triangulations of the n-gon times the product of 1 over all the xij's where ij are chords inside the triangulation. Okay? Is that clear? So for instance, if I drew the pentagon, which is dual to this diagram, then I would write, this is the one that we talked about before. I'd write 1 over x13, that guy, and 1 over x14. Okay, but I sum over all possible triangulations. Okay, so this is the answer. So this is our kinematic space, just the space of all these x's. This is the answer we're supposed to get. If our name is Feynman, this is the answer that we give. And now we have our well-posed question again. I only have the space of xij's. I don't know anything about the interior space-time, Feynman diagrams, anything. What question can I ask on xij space whose answer is that? Okay, so this is our cousin of the amplitude problem for this much, much simpler theory. Just scalars, no momentum twisters, no fancy k, no super anything, any number of dimensions. In fact, this formula really makes sense in infinitely many dimensions because in any fixed number of dimensions, there's additional relations that are satisfied between these invariants that tell you that if you take enough, four-dimensional vectors, if you take 10 four-dimensional vectors, they satisfy lots. They're all linearly dependent. Okay? So here I'm not taking any of the linear dependencies, the so-called grand determinant conditions. I'm not taking any of them into account. These are the formulas that you just get on the nose in any number of dimensions without taking the dimensionality of space into account. So that's what's a little bit funny. The kinematic space here is just a space of Mandelstam invariants. It doesn't know about the dimensionality of space-time. But now we want to ask a question in this space whose answer gives us that. And I just want to spend 5 minutes and then we can go. I won't do any formulas, but just to give you an invitation now in this simpler setting for why it is that for something this stupid, we might still be missing something. For a long time, I had the prejudice that I think many people in the amplitude business have the prejudice that all the magic in amplitudes was somehow for Yang-Mills theory and gravity, which are the theories where, in the conventional way of doing things with Lagrangians, you start having to make lots of excuses and introduce all sorts of baggage and so on. But I certainly thought something as stupid as phi to the fourth theory or phi cube theory, what you get from the Lagrangian cannot be beat. Right? What is there left to be desired? Okay? For n equals 4 super Yang-Mills, even in gravity, but certainly not for n equals 4 super Yang-Mills, we eventually found these hidden symmetries, like dual conformal invariants. Right? That's a miraculous hidden symmetry of n equals 4 super Yang-Mills. It's definitely not obvious in the Lagrangian. And you would have never thought there was any kind of hidden symmetry in something as dumb as phi cube theory. Okay? Well, that turns out to be wrong. There is something in phi cubed. Even in dumb old phi cubed, there's an analog of dual conformal symmetry. There's a hidden structure, and we're going to see it. It's all going to be exposed by connecting this very simple physics to this philosophy of thinking about amplitudes as answers to questions in kinematic space. And doing that is going to connect, and it should not be a surprise at all to those of you who have been coming to this workshop or even seeing the last few days of the lectures, that this question is going to be connected with the isosahedron in an interesting way. So the isosahedron is this polytope that captures the combinatorics of all the triangulations of an n-gon. Here, we're just sort of summing over all the triangulations of an n-gon of something that looks like it cares about all the pieces in the triangulation. This is why, when I first learned about anything to do with any of these fancy things 10 years ago, I learned what the isosahedron was, and I was immediately, that should have something to do with phi cube theory, obviously. But we're obstructed for a long, long time to figure out how to do it, because the key idea that was missing is this idea of amplitudes as differential forms in kinematic space. Once you have that idea that amplitudes are differential forms in kinematic space, it opens up a way of thinking about things in this way, much, much more general. So we're going to see that. But let me just say, in just 2 minutes, what this invitation for why there is something missing. Why there's something missing is this. We said we're cheating to get this answer, right? But let's imagine we didn't know that's the answer, and imagine that we're this experimentalist that was sitting at infinity. All this experimentalist does is they move the xij's around, and they want to see what this mysterious gadget is that they have. They don't know there's an inside of the space-time. They're moving the xij's around. What do you think they're going to notice first about these amplitudes? They measure these amplitudes. What do you think they're going to notice about the amplitudes? Obviously, the first thing they'll notice is where they blow up. Okay, so the amplitudes are going to have poles in certain places, and the experimentals are going to be excited about that. Okay, great. So the amplitudes have poles somewhere. So they have poles when some xij goes to 0. And now what they do next with this information depends on the kind of experimentalist they are. I like to say that there are experimentalists who are closet theorists and real experimentalists. But the closet theorist experimentalists say, aha, there's a pole. So I should very carefully measure what the residue of this pole is. So I go in the neighborhood of that pole, I measure everything about what happens when I move the other variables around, and what do they discover if they do that? They discover there's a miraculous fact about the residue when xij goes to 0. It factorizes into the product of lower things. And that's something which is sort of obvious from Feynman diagrams, but when a given xij goes to 0, in terms of the cubic graphs, one of these internal lines is going to 0, and you get a factorization. Right? You get a 1 over the corresponding pole, and then you get this factorization. In the language of the polygon, when this xij is going to 0, the residue is 1 over that xij times the function you would have gotten for this upper polygon times the lower polygon. Okay, so what this person gets excited about is factorization. So on this side, what you get excited about is factorization. And you go to your favorite conference where you're supposed to announce your experimental results, and you tell the theorists in attendance, I've discovered this incredible thing, this function as I move around, it factorizes into 2 pieces. What do you think is going on? What's the theory? So this is surely a clue to the theory, and it is indeed a clue to the theory, and Feynman sitting there in the audience takes this clue and says, aha, I know what's going on. What's going on is that I'm summing over Feynman diagrams that I've now named after myself. Okay, and they say, okay, great. So that explains this. That's what's going on. Of course, there's all this redundant crap in the middle that's not there, but I don't care. I'm just going to say that I'm summing over all these diagrams, and this makes factorization obvious. But some mathematician in the audience, someone who knows about Deline, anyone who knows about the configuration space of endpoints on P1 would say, oh, I know this, I've seen this before. This is just what happens for endpoints on P1. And the boundary of endpoints on P1 factorizes exactly the same way. So this must be what's going on. Somehow your problem has to do with endpoints on P1, and the fact that it factorizes is reflecting this sort of famous, beautiful fact that the space of endpoints on the boundary of a disk, its boundary factorizes in this way. Okay, and both of these reactions to factorization are associated with physics words. Okay, this is the picture of particles in space-time, and this is string theory. This is the string worldsheet, which is just to say that if factorization is the star of the show, if that's what you've gotten excited about, then that's what physicists have been excited about for 50 years, and the 2 classic ways we know of talking about scattering amplitudes involve ways of making this fact obvious. Particles in spacetime make it obvious, the string worldsheet makes it obvious. Okay, but there's a smarter but lazier experimentalist who is the hero of my little parable here. Okay, and they don't know about residues. They're very lazy. They don't want to just sit there and do these very careful measurements of what happens near a pole. What do they do instead? They're like kids. They say, I make something blow up. Making it blow up was really fun. Let me try to make it blow up more. Right? So they take these x's, they set some of the x's to 0, they say the amplitude blows up, they say, now what can I do if I set more x's, can I make it blow up more? In other words, they want to see the chain of poles that they can encounter as they're moving these invariants around. And then all they do is they make a big list of what are those chains of poles that they saw. For example, for n equals 4, they would say I can have x13 or I can have x24. For n equals 5, they could say I can have x13, but then I can also have x13 and x14. Or I could have x13, or I could have x13 and x35. So they just make lists of the single poles that are allowed, the double poles that are allowed, the triple poles that are allowed, and so on. And that's what they care about. And they look to see if there's any qualitative pattern in that stuff. And the qualitative pattern in that stuff is that the list of single, double, triple, etc. poles are precisely associated with facets of the isosahedron. This is a remarkable fact that, you know, the sort of many mathematicians are used to it now. Certainly Jim Stashev wasn't used to it when he discovered it. Okay, this is a quite remarkable fact that the combinatorics of triangulations of a polygon is polytopal. That there is any polytope associated with it at all. That's kind of amazing. That's what it looks like for n equals 6. I certainly wouldn't have guessed it out of the box, and I could take all these pictures and glue them together into this sort of amazing looking object. Okay? So this second experimentalist is like, wow, this is the most amazing thing in the world. I take all the sequences of poles that I see. The first poles are the faces, the second poles are the edges, the three poles together are the vertices of this guy, and it's incredible that they're related to each other in this way that's captured by a polytope. Maybe they're smart enough to draw this picture for n equals 3. Even if they can't draw the picture for higher n, they can just count how many of these things they have and do the relevant Euler sums and see all the Euler sums add up to 0, right? And say, wow, maybe there's a polytope that's associated with this. Okay, now what I want to say is that this second fact, which is what this laser experimentalist notices, right? They're not doing any detailed measurements of anything. It's something almost purely combinatorial. They're just looking at what are the sequences of how you can make things blow up. This is a qualitative fact, which is not made obvious by either Feynman or by the string worldsheet. And this is not something, well, and the proof is that if you ask a random physics grad student whether they realize this fact, the answer is no. This is in none of the textbooks. We don't know that this is just not something we even think about. Okay, so this is a second qualitative fact about the answer, which is hidden in our standard way of thinking about things. The remarkable thing is, if you know this fact, you actually get the other one. Okay, because this polytope is not a random polytope. It has the property that, on its faces, its facets look like direct products of lower polytopes of the same type. So the fact that it's polytopal and that the boundaries factorize into lower polytopes of the same type captures everything there is to know about the problem. Whereas factorization alone is missing the polytopal nature of it. Okay? So this is just an invitation that there is more to be discovered. That there's more, even for this dumb old phi cube theory, there's more to be discovered. And that's what we'll talk about when we come back after lunch. Okay, so I'm going to go back to this kinematic space of xij's and now begin asking similar simple questions and discovering the isosahedron along the way. Okay? This is going to end up leading us to a way of thinking about all the cluster polytopes along the lines of what Hugh Thomas and his students did as a generalization of what we talked about earlier just for isosahedra, but in a way that at least begins from a very familiar starting point for a physicist. And after we get that under our belts, we'll move on to discover string amplitudes. All right, thanks a lot.
Why do you have this all particles on this circle and not on the sphere?
Sorry? We can also have all the particles on the sphere, and that's gravity. Okay? And they're really a kind of a mysterious thing, which is it's extremely. This is what you're asking is a super deep question. Okay?
Why you
Because
have a real model in space?
no. It's a super deep question. I mean, I think this is a billion-dollar question in this subject as far as I'm concerned. You see. Like string amplitudes really are. They're really on the surface of a sphere, not the surface of this. We're doing closed strings and not open strings. These things all have an ordering. It's like they have color, like Yang-Mills and so on. If you're literally doing gravity, you're just 4 points on a sphere. Now here's the annoying thing. All of this business where we relate geometry to amplitudes, forms, and so on, the sort of key idea is some kind of form of singularities, maybe logarithmic singularities of some sort, associated with boundary strata of some real space. Complex form maybe, but boundary strata of all the real space. So the boundaries have to go down 1 in codimension, right? You want to take residues, you go down. So that's why we have like polytopes, polygons, polytopes, amplitude generalizations, but there are things that have boundaries in all codimension. The problem with 4 points literally on the real sphere is that the factorization, the boundary that we want, where it splits like that, is not codimension 1 as a real codimension. It's codimension 2. So somehow, whatever idea, we need to have some kind of intrinsically, if we want to have an, and that's why even in string theory, the way you think about closed string amplitudes is the square of open string amplitudes. So it's really, the basic object is really the sort of open string, and then you do things with it. You can decide the square and integrate over the whole real thing and so on. But all of the geometry is, and this sort of D-log geometry is either for open strings with real variables, or you then mod square everything and you interpret that as something for the closed, but there's not an intrinsic closed picture where you can see the sort of, and this is a very essential difficulty, that when everything is real, somehow the boundary structure goes down in steps of 2. And we don't know how to capture that. So it's an excellent question. The fact that we don't know how to answer that is why we're stuck talking about gravity in every theory we're talking about, where we have some understanding of it, roughly is the square of Yang-Mills, which sucks. Okay? It actually sort of sucks because gravity is much more interesting than that. Vastly, vastly more interesting than that. But that's the best we can do right now. It has all sorts of properties that are obscured when you write it that way, that only come out in some emergent way. But that's a wonderful question. Are you happy now, Yara? Any other questions before we eat? Okie dokie.